This is the Transition Series Topics for the EMT, Topic 8, Blood, Cardiac Function, and the Vascular System. Our objectives are to identify the components of blood volume, identify the roles of hydrostatic pressure and plasma oncotic pressure, determine the variables that play into cardiac output, identify the variables that affect systemic vascular resistance, and discuss the roles of the autonomic nervous system in perfusion. Many variables must interact in a particular way for normal perfusion. Perfusion is the delivery of oxygenated blood and glucose to the cells and removal of carbon dioxide and other waste products. For perfusion to be adequate, oxygen must enter the alveoli, cross across the alveoli capillary membrane, attach to a hemoglobin molecule, and be transported through the blood to the cells. The blood composition, cardiac function, and vascular resistance all contribute to the movement of oxygenated blood out of the alveolar capillaries and to the cell beds. Blood is mostly water. 55% of the blood is plasma. 91% of that is water. Albumin, antibodies, and clotting factors make up the balance. The other 45% of the blood is the solid or formed elements. This is referred to as the hematocrit and includes red blood cells, white blood cells, and the clotting cells referred to as platelets. Blood is distributed throughout the body in arteries, in veins, and in organs as follows. 64% of our blood volume at any one time is in the veins. 13% of the blood volume is in the arteries. 9% is in the vessels of the lungs, the pulmonary vessels, and 7% is in the capillary beds. The remaining 7% is in the heart. Hydrostatic pressure is the pressure created by myocardial contraction, by the contraction of the heart, and vasoconstriction that opposes it to create blood pressure. Hydrostatic pressure tends to force blood out of the vascular space and into the tissue beds. Disturbances in hydrostatic pressure can create emergencies. Too high or too low hydrostatic pressure can result in inadequate or excessive movement of fluid from the bloodstream and into the tissue beds. Plasma oncotic pressure is the reverse. It's the force exerted by large plasma proteins in the blood vessels. Because water tends to equalize across solutions, moving from areas of low concentration to areas of high concentration, these large proteins tend to draw water into the vascular space, keeping enough fluid in the blood. High hydrostatic pressure tends to force fluid out of the blood. Low hydrostatic pressure leaves it in the blood. High oncotic pressure tends to draw fluid into the blood. Low oncotic pressure tends to leave it in the blood. Here's an illustration. In the artery and arteriole, high pressure blood moving from the heart enters a capillary. Every cell in the body lies alongside a capillary, providing oxygen and taking away carbon dioxide, bringing in nutrients and taking away waste products. The hydrostatic pressure in the capillary tends to push water out into the cell. The plasma oncotic pressure in the capillary tends to draw water out of the cell. This is a constant balancing act. For the heart to work effectively, it must have sufficient stroke volume, or the amount of blood that's ejected with each pump, and a sufficient heart rate. Normal heart rate is somewhere between 60 and 100 beats per minute. Normal stroke volume is about 70 milliliters. Stroke volume is affected by the preload, or the amount of blood available to the heart, the contractility of the heart, the pressure with which it ejects blood from the ventricles, and the afterload, or the pressure in the arteries against which the heart is ejecting. An increase in heart rate will increase the amount of blood being ejected. An increase or decrease in blood volume will affect the amount of blood being moved through the system. An increase or decrease in the contractility of the ventricles will increase or decrease the amount of blood being ejected. An increase or decrease in sympathetic tone will cause the heart to beat faster and stronger and the peripheral vessels to contract. A decrease in or increase in parasympathetic tone will cause the heart to slow down and cause the peripheral vessels to relax. The systemic vascular resistance is the remaining component of blood pressure. Cardiac output is defined as stroke volume times heart rate. That's the amount of blood flowing out of the heart. If there's no resistance, however, blood pressure will drop rapidly. There must be a certain amount of resistance presented to the blood volume, and that resistance is maintained through vasoconstriction, or constriction of the vessels, and vasodilation. It's also affected by changes in autonomic tone. Sympathetic tone, the fight or flight reflex, causes the heart rate to go up and the peripheral arteries to constrict. Parasympathetic tone causes the heart to slow down and allows the capillary beds to relax and open and allow blood to flow through them. These systems are referred to as the fight or fight and the rest and regenerate systems. So, systemic vascular resistance is the amount of pressure being exerted by the body back against the ejected heart volume. Pulse pressure is the difference between the top pressure, or systolic pressure, and the diastolic pressure. So the pulse pressure of a patient with a blood pressure of 120/80 is 40 millimeters of mercury. Vasoconstriction tends to cause the blood pressure to increase. Vasodilation tends to cause it to decrease. For example, when a patient's fight or flight reflex is stimulated, the sympathetic side of the autonomic nervous system is triggered, and the heart rate increases, and the peripheral vessels tend to close down, except for the large vessels in the arms and legs, which must be expanded to allow for us to fight or flee. If we do neither, if we just stand, those dilated vessels will cause us to faint, to lose sufficient blood pressure to pass out. Pulse pressure changes can be caused by conditions such as pericardial tamponade, which decreases the ability of the heart to eject sufficient blood with each contraction. Microcirculation is the flow of blood through the smallest blood vessels, the arterioles and venules in the capillary beds. Microcirculation is affected by hormones such as adrenaline and by the autonomic nervous system through the nerves, which may cause capillaries to dilate and cause the capillary sphincters, shown here, to dilate, to allowing pressure in or not allowing pressure into the capillaries. I want to reinforce here that every cell in the body lies alongside a capillary. Capillaries are extremely small, just big enough for one red blood cell at a time to move through them. Red blood cells are so small that there are 5 million red blood cells in a single milliliter of blood. Again, blood pressure is the sum of cardiac output times the systemic vascular resistance. To maintain adequate perfusion, blood must be pushed with enough force to constantly deliver oxygen and glucose to the cells and remove carbon dioxide and other waste products. Generally, an increase in blood pressure will increase cellular perfusion, and a decrease in blood pressure will decrease cellular perfusion. Baroreceptors in the blood, or rather in the carotid arteries, detect the amount of pressure in the blood and give feedback to the brain, allowing the nervous system to adapt and relax the peripheral vessels or increase the heart rate as necessary to keep blood pressure constant. Chemoreceptors in the bloodstream detect changes in the blood chemistry, such as the amount of oxygen, the amount of carbon dioxide, and the concentration of hydrogen ions or acidity. In summary, along with maintaining oxygenation, the body must sustain adequate blood pressure for peripheral perfusion of the capillary beds. In situations where peripheral perfusion is poor, blood may be shunted to the core organs. This is why the skin becomes gray and colorless in shock. Early identification of a failing cardiovascular system both underscores the need for rapid transport and should alert us to potential problems that the patient may face.